Good morning, everyone. Are you able to see my screen?
Yes, once I do this for the group here. 1 second. I don't know how to get that better. Okay, yeah, we can see your screen okay. You can go ahead.
All right. Good morning, everyone. Very interesting presentation by other colleagues. I'll talk about residual strength assessment of a fire damaged steel I-Girder from Erasburg, Vermont bridge fire that happened in December 2023. I'm a metals research engineer at Turner Fairbank Highway Research Center. Just a quick disclaimer that the opinion provided in this presentation are my own and they do not necessarily reflect those of FHWA or US Department of Transportation. I'll quickly talk about background and then the problem statement, then the methodology that we designed in order to achieve our objectives. And I'll provide a couple of quick results and also discuss the ongoing work. Last year in winter, there was a fiery crash on VT14 bridge. There was basically a 10,000 gallon propane tanker that went off the bridge, and then there was fire for almost 36 hours. The fire was, as you can see in the middle figure, it was like 5 to 10 feet away from the bridge girder. And it caused significant distortion in the exterior girder. It caused dig sag, and it caused significant damage to the interior abutments as well. Based on the damage that was seen after the fire it was extinguished, we decided to replace the bridge as well as the abutments. Here I'll discuss that whenever there is a fire, steel structure is affected by fire, so we can categorize the fire-affected structure into three classes. Class 1 or category 1 are those steel structures where we do not see any noticeable deformation in the members, as you can see in one of the figures on the left side. Whereas category 2 and category 3 are those steel structures where we see either noticeable deformation in the members or severe deformation in the members. Usually category 2 are those type of structure that we can repair. Even category 3 can be repaired if they are repairable, if there is not too much deformation. FHWA has a manual that we can use for repairing such structures. This manual has been in existence from 90s. Last year there was an updated manual, which is FHWA manual for heat straightening, heat curving, and cold bending of bridge component. We use this manual in order to repair a fire damaged girder from Brent Spence Bridge. That was one famous fire that occurred in Kentucky. Eventually that bridge was replaced, but I'll show you that we can use heat straightening to repair a bridge, to repair a fire affected member. We can essentially remove all the distortion, as you can see in this video. So we have a few questions about this girder, which constitute our problem statement. It is that what is the residual capacity of the steel? Did the fire cause any metallurgical phase changes in the steel, because those could be detrimental for mechanical properties? And could this steel girder have been repaired? Although this, because of the complexity and because of the difficulty ensuring the bridge over and performing the repair of the waterway, V-Trans decided to replace this bridge girder, but we received the fire damaged girder, and we are investigating it further to answer these questions. So the first step in the methodology was to perform geometric laser scanning and determine how much is the actual deformation that occurred as a result of fire. And our laser scanning that we did, it showed that flange has a maximum sweep of 11.6 inches. In all other locations, the distortion was less than this value. However, there was a lot of local buckling as well. Using the results that we got from the laser scan, we decided the zones that have maximum distortion. We also decided what zones are those where there is almost no fire damage. And subsequently, we determined the microstructure properties of those zones. And as you can see in this photo, in this slide, the first photo show typical microstructure of a steel, where we see the white portion presenting ferrite and the dark portion presenting pearlite. The next photo shows the after fire photo or the fire damaged steel photo, the microstructure, and we can see there is significant increase in the grain size. There is almost 3 times increase in the grains that we are seeing. However, luckily, we did not see any metallurgical phase changes. That means that the steel property would change, but they would not change abruptly. We also look at, because this is a weathering steel, so we are also interested in seeing what happened to the patina layer and how it is going to help how it is not going to help corrosion in the future. We saw that there was substantial increase in the thickness of patina layer. As you can see, if you compare the patina layer of the virgin steel with the post-fire steel. In the virgin case, it was almost 2 mils, 55 micron, and there was almost 8 times increase in the thickness of this layer. We are still in the process of characterizing this layer, the integrity as well as the chemical composition of this layer. Going forward, we obtained coupons and CVNs and other steel sample from different locations of this girder, and we are going to carry out tension test, impact test, hardness test, as well as chemical analysis. So just to summarize the most important findings that we obtained thus far from this work is that prolonged fire exposure in this case caused approximately 11.6 inches of flange sweep. Fire exposure resulted in nearly 3 times increase in the steel crystal sizes, that is ferrite and pearlite grain sizes. However, we did not see any metallurgical phase changes such as formation of martensite or benite. And then the uncoated weathering steel's protective patina layer increased in thickness by almost 8 times as compared to the normal thickness during the fire. The ongoing work include patina layer characterization and obtaining mechanical toughness and hardness properties of the steel before and after fire damage. The benefit of this work is going to help us, basically the results are going to help us that if we have a similar fire on a steel girder or steel bridge, and the damage is bound within the ranges that we just saw in one of the slides. So we can potentially use the results that we get from here and decide whether we can repair or whether we need to replace a bridge girder. Thank you very much for your attention. If you have any questions.
Good. I've got one question, if I may ask.
Yes.
Very interesting presentation. So when we are repairing, these fire damaged new steel girders, once they are repaired, can we just assume that, it is restored to the original mechanical property? Or, for example, when we are doing load rating, we gotta take that into account that, hey, this is, a repaired fire damage, for example, a steel girder.
Yeah, okay, that's a very good question. And this is what we were also wondering when we were testing the steel girder from the Brent Spence Bridge. In that case, we also had like 8 inches of sweep. And we dumped a lot of, there was fire damage and then there was heat dump during the heat straightening. Interestingly, we saw that as long as you are staying below 1200 degree Fahrenheit, so that means you are not going to change the phase in the material.
Interesting.
And then FHWR manual, it has a very detailed procedure where it tells you that, how much jacking forces you should apply. The point is that we don't want to do any cold working or any mechanical working.
Right,
We
right.
just want to use heat in order to straighten. And we recently published a paper on that bridge, and we observed that there is like less than 10% reduction in the yield strength. The ultimate tensile strength is almost within 5%. And the toughness values that we were getting, they were also within the AASHTO limitation, like the AASHTO recommended limits for fracture and non-fracture critical members. So based on the results that we have obtained for the Kentucky bridge and also like the bridge that we are currently working on, we can say that the effect is not significant.
I see.
However, I would like to caution that it depends on bridge to bridge. It depends on whether there has been any phase change or not. If there is no phase change, and if the procedure is correctly followed, if the cooling rates during the heat straightening repair, they are not rapid, so we should be good.
Okay, got it. Thank you very much.
Yeah.